Okay, welcome to this video. In this video I'd like to derive the equation for centripetal acceleration. Okay, and we know that centripetal acceleration A is equal to v squared over r. So where did we get this from? Well, let's draw a quick diagram. I don't have a compass to hand, so I'm just going to use my Bluetooth speaker here just to draw around that. And it's not going to be very accurate, but we don't need it to be because we're not doing any calculations with this. Where is the center? It's approximately here, and we've got an object, maybe a ball, moving around the outside of a circle that we've swung, and it's got a velocity of v. Okay, if I can just, and then it's going to move through a position. It's going to move through an angle to position 2. And we're still going to be moving with velocity v. But even though the speed has remained constant, the velocity has changed because velocity is a vector, and it's not just dependent on speed, it's also dependent on the direction. We can see here that the direction has changed, which means we've got a change in velocity. And the definition of acceleration is change in velocity divided by the time taken. And that's what we want to investigate here. So it's moved through an angle theta, and it's changed position through a distance. We're going to call that delta x in time delta t. Okay, so what can we say from that? Well, we know that a couple of things. Well, we know that delta theta, or the change in the angle, is equal to the arc length divided by r. Okay, so in this case, the arc length, or the distance traveled, is delta x, and r is the radius there. So that's our first equation, or we can say delta x is equal to delta theta r, or theta r. Okay, that's our first equation. We also know v is equal to the distance traveled divided by the time taken, and we can also say there that or delta x equals vt in that case. Okay, but we're really interested in change in velocity. And how can we work out the change in velocity? Well, we need to draw a vector diagram tail to tail. What we're saying is that theta is, as it tends to 0, as it becomes really small, that this distance here is equal to the arc length. So as theta tends to 0, or as theta delta v is equal to arc length. And what can we say then? This distance, so theta here is equal to delta v divided by v. Okay, so that gives us our change in velocity, or delta v is equal to theta v. Okay, so what can we say here? Well, we've got equation 1, we've got equation 2, and we've got equation 3. Let's work out what we know from the rearranging these equations. Well, let's start with the first one. Delta x equals delta theta r. And delta x here is also equal to vt. Okay, and we know here that delta theta, or theta, is equal to delta v over v. Times r, which is equal to vt. But we really want to know what acceleration is, and we know acceleration is equal to change in velocity over time taken, isn't it? Yeah. So we want to get this. So by rearranging that, we can get we can put the v up here. Wait, what do we want? We want the v up here and we want the t down there, and then we want to get rid of the r. So by doing that, we get delta v divided by t equals v squared, and then r is at the bottom. This is of course equal to a, so our final answer is a equals v squared over r. Okay, I hope that's helped you with the derivation. Please stay tuned for more videos.